Welcome back to AI.Code.Cast. Ready for another deep dive? Today's is a real brain teaser. It's called the largest number problem.
It's a classic.
Sounds simple at first, but it's got some tricks.
Oh yeah, it'll make you think about sorting in strings in a whole new way.
So give us the rundown. What's the problem all about?
All right, imagine you have a list of integers, all non-negative.
Okay, like 1, 5, 20, that kind of thing.
Exactly. And your goal, your challenge, is to figure out how to arrange these numbers to make the absolute biggest number possible.
Interesting. So if we had like 3, 9, and 1, the largest number would be 931.
Right. But there's a catch. The result has to be returned as a string.
Ah, a string. Why is that?
Because these numbers, they can get huge EE. We're talking potentially way too big to be handled as regular integers in most systems.
Okay, that makes sense. So if we're dealing with massive numbers, my first thought would be to just sort them, in descending order, biggest to smallest. Done, right.
Seems logical, doesn't it? But let me throw a curveball at you. What if you only had two numbers in your list? 3 and 30.
All right, so sorting those, biggest first, would give me 30 then 3, which makes 303.
Precisely. But if you flip them around, you'd have 3, then 30, making 330.
Whoa, yeah, way bigger. So it's not as simple as just sorting the numbers themselves.
Nope. It's all about how those numbers look when they're combined side by side.
I'm starting to see why this is a tricky one. It's not just about the individual size of the numbers, but about their relationships to each other.
You're getting it. Now, before we dive into the really clever solutions, let's talk about that first instinct you had, just trying every single possibility.
Good old brute force. It's tempting. Just try everything and see what sticks.
It's tempting, but in this case, it's a recipe for disaster.
How so?
Think about it. Brute force would mean generating every single permutation of those numbers, every possible arrangement.
Yeah.
Then you'd have to turn each permutation into a string and compare them all to find the biggest one. The more numbers you have, the worse it gets.
Sounds like a computational nightmare.
It is. It's what we call factorial complexity. Let's say you have 10 numbers. The number of ways to arrange them is 10 times 9 times 8, and so on, all the way down to 1. It gets huge E fast.
Yeah, brute force isn't going to cut it, especially if we're dealing with those massive numbers we talked about.
Exactly. We need a smarter approach, something that considers how the numbers would look strung together as one big number.
Okay, so instead of asking, is 3 bigger than 30? We need to be asking, would 330 be bigger than 303?
Now you're on the right track. That kind of comparison, looking at the strings they make together, that's at the heart of the solution. But the question is, how do we use that to sort our numbers in the right way?
Well, if we're thinking about strings now, could we maybe tweak a sorting algorithm to use our new string-based logic?
You're getting warmer. We can absolutely leverage sorting algorithms, the powerful ones like merge sort or quick sort, but we need to give them a special set of instructions.
Special instructions how?
We need to tell them how to compare those strings, and that's where a custom comparator function comes in.
A custom comparator. Interesting. So instead of directly comparing the numbers, our sorting algorithm would use this function, this comparator, to compare the strings they'd make.
Exactly. The comparator becomes the rule book for the sorting algorithm. It dictates how to decide which string should come first.
Okay, starting to see the pieces come together. We convert the numbers to strings, use a sorting algorithm with our custom comparator, and boom, sorted list based on our string logic. What happens next?
Well, let's break down how that comparator would actually work. Picture this. It's looking at two strings. Let's call them A and B. What should it do to figure out their order?
I think I've got this. It should compare A plus B to B plus A. Whichever is bigger, that's the one that comes first, right?
You nailed it. That's the essence of our custom comparator. It's all about comparing those concatenated strings.
Okay, so I think I get the big picture. But before we jump into specific code, are there any, common traps people fall into with this problem? Things to watch out for?
Oh, absolutely. Remember that case we talked about? The one where all the numbers in the list are 0?
Right. If we're not careful, our code might end up giving us something like 0, 0, 0 instead of just a single 0.
Exactly. We need a specific check at the end to handle that kind of edge case. And of course, there's the classic mistake of forgetting to convert those numbers into strings before doing any comparisons.
Yeah, if we try to add those integers together, we'll get a numerical sum, not the string combination we're after.
Right. So just a couple of things to keep in mind as we move into the implementation details. Speaking of which, how about we explore how this would play out in Python?
Sounds good to me. Let's see how Python tackles the largest number problem.
Python, it's perfect for this. It's got some really neat tools for working with lists and strings.
Okay, so how do we, actually solve this problem in Python?
Python has this handy built-in function. It's called sorted. It does the heavy lifting of sorting for us.
Okay.
And here's the cool part. We can give it a custom function, our comparator, to tell it how to sort.
Ah, so we don't have to code up, the whole sorting algorithm ourselves.
Exactly. We just got to tell sorted how to compare those strings we've created.
And how do we do that? How would this custom comparator thing look in Python?
Well, Python lets you define a function right inside another function. They're called Lambda functions.
Lambda functions. I think I've heard of those, but haven't really used them.
Perfect for small tasks like our comparator.
So instead of writing a whole separate function just to compare two things, we can kind of sneak it right into the sorting process.
Precisely. Very efficient.
Got it.
So our Lambda function, it takes two strings. Let's call them x and y. Simple.
Okay.
And it compares x plus y with y plus x, just like we discussed. Right?
Yeah, and then it tells sorted which string should come first based on that comparison.
Yep. And that's pretty much it. Of course, don't forget about that zero edge case. Got to handle that separately. Just check at the end.
Right. Return 0 if all numbers are 0. Good catch.
Yeah.
So in Python, it's basically convert to strings, sort with our custom Lambda comparator, and then handle that special 0 case.
You got it. Python makes it so clean. But what about other languages? Like C#, for example. Some people might be using that.
Yeah, C# feels a bit more structured than Python.
It is. It is.
Would we solve this problem in a totally different way in C#?
The core idea is the same. The syntax is a bit more involved, though.
Okay.
In C#, we'd implement an interface, specifically the iComparer interface.
Interface. Now, remind me what that is again?
Think of it like a contract.
Okay.
It tells a class, hey, if you want to do this job, you got to have these specific methods. And the iComparer interface, that's specifically for custom comparators.
So by implementing this interface, we're basically telling C#, hey, trust us. Our class knows how to compare these strings properly.
Exactly. And to, fulfill that contract, we got to define a method in our class. It's called compare.
Okay.
And that method, that's where the comparison magic happens.
You see, so it's like our Lambda function from Python, right?
Yeah.
This compare method, that's where we put the code to check which combined string is larger.
Exactly. The logic inside is identical to what we did in Python. Take two strings, A and B, combine them both ways, see which one comes out bigger.
So it's like a whole separate class with a special method instead of a quick little Lambda function. A bit more work, but same idea.
Precisely. Then, just like in Python, we'd use this custom comparator with our sorting algorithm, make sure those strings are in the right order.
All right, so whether it's a Lambda function in Python or a class with this compare method in C#, the big idea is the same. Custom rules for sorting. It's cool.
It is. Now, before we move on, we got to talk about how efficient this solution is. Remember that factorial complexity thing?
Yeah.
With the brute force approach?
Yeah, that was scary.
Yeah. How does our custom comparator solution measure up?
Good question. Is it any better?
Much better. The time it takes, it's mostly determined by the sorting algorithm itself. And good algorithms like merge sort or quick sort, those are pretty fast.
Okay, so what's the time complexity?
O(n), log n, where n is the number of integers we're dealing with. Much better than factorial.
Way better. Phew.
Yeah.
What about space complexity? All that string stuff, does that take up a lot of memory?
We need space to store those strings, of course, so that's
Oh.
O(n). And then the final string, the result, that's O(n) too.
So still linear space complexity. Not too shabby.
Nope, not too shabby at all. We've gone from a potential nightmare with brute force to something much more manageable.
Huge improvement. Really shows how powerful that custom comparator idea is. Makes things cleaner and more efficient.
It's a win-win. But before we go, I think we should explain that x times 10 trick.
Oh yeah, that sounded kind of mysterious. Why do we multiply by 10 in Python? Does that really help us compare the strings the right way?
It does. It's all about how Python compares strings. You see, that goes character by character. So let's say we're comparing 3 and 30.
Right.
If we just combine them directly, 330 is obviously bigger than 303, which is what we want. But what if the differences are less obvious?
I see. So we need a way to make sure Python considers those later digits too.
Right. And that's where multiplying by 10 comes in.
Okay, I'm listening.
Imagine Python's doing this comparison. It takes 3 and multiplies it by 10. You get like 3.
It repeats the digit.
Exactly. And it does the same with 30, turning it into 303030303030303003.
Okay, so by repeating the strings, even small differences become clear. 33303030303030303330.
You got it. That times 10 trick, it kind of forces Python to look at the whole pattern, not just the first few digits.
Clever. It's like we're tricking Python into doing the comparison we want.
Exactly. So to recap our Python approach, convert the numbers to strings, sort using sorted with our Lambda function and that little times 10 trick, and then handle the case where everything is 0. Pretty slick, huh?
Very slick. Python's pretty powerful when you know how to use it. But I bet some of our listeners are using other languages. Would this work in other places?
Absolutely. The core ideas are the same. Java, JavaScript, they all have ways to create custom comparators. Sometimes it involves interfaces. Sometimes you pass comparison functions to sorting functions.
So the key is that no matter the language, we're still sorting based on those combined strings.
Right. The details might be different, but the approach is universal. And I think this problem shows us something really important. Thinking about sorting in unconventional ways can be super helpful.
Totally agree. We're used to sorting things, from smallest to largest or vice versa.
Yeah.
But this problem makes us break free from that.
Exactly. And custom comparators, they're not just for making big numbers, They're useful in so many other places.
Oh, yeah. Like where? Give us some examples.
Imagine you're building an app, a to-do list app.
Okay.
You might want to sort the tasks by due date, but also by priority. So a high priority task, even if it's due later, it should be higher on the list.
That makes sense. Or like
Sure.
sorting a music library. You might want to sort by genre, then by artist, and then by album.
Exactly. Custom comparators give you fine control. You can sort things however you need to.
It's amazing, isn't it? This problem, it seems so specific at first, just arranging numbers to make a big value. But it leads to some really powerful ideas about sorting in general.
It does. It does. It shows how exploring these kind of niche coding problems can teach you things that apply in so many different areas.
I love that. Well, I think that about wraps up our deep dive into the largest number problem. We talked about what the problem is, why brute force doesn't work, and how to use a custom comparator to solve it in a really elegant way.
We even looked at how to do it in Python and C#, and we talked about why it's so efficient.
Plus, we got to see how powerful custom comparators are and all the cool things they can do.
Hopefully our listeners are feeling inspired, ready to tackle their own tricky sorting problems.
That's what we like to hear. Thanks for joining us on AI.Code.Cast. Until next time, happy coding.
Keep those brains buzzing.